Yeah, today I'm gonna just briefly talk about this final project. It actually consists of a report as well as a presentation. So for final, we don't have any exam. Okay, we are gonna just focus on the project. So here are the objectives of the project. You can kind of take a look at this one. These are essentially kind of also included as a part of rubric for evaluation. But anyways, the report, basically, each student will write an individual mini review article. Okay, so think about this as kind of prepping for your thesis work. And this article should focus on a specific nanomaterial or class of nanomaterials. Okay, so, and then for that one, you are gonna kind of choose a topic, you would like to pursue, and then you are gonna explore its unique properties and also scientific principles that govern those properties and the method used to characterize or evaluate the material and its implications for naval or Department of War applications. Okay, so and then for this one, the length should be like a minimum 15 pages and maximum 25 pages. Okay, this includes the figures and references. And then the format is a letter size paper and double space 12 point Times New Roman font and a 1-inch margins on all sides. Okay, and then for references, so you have to find out minimum 20 peer-reviewed articles. Okay, so and deadline is essentially 2 p.m. Of the last day of the lecture. Okay, and then the soft copy must be uploaded to Sakai. So in terms of topic selection, you can choose any topic you like. Okay, and I actually strongly encourage you guys to select one that is relevant to your thesis paper or personal interest. Okay, so if you can actually choose the topic that is somehow relevant to your thesis work, that is actually very desirable, because think of this as kind of some level of preliminary work or kind of literature body search. Okay, so but based on kind of my previous experience, actually many students kind of find one topic interesting, and then multiple topics are chosen, even within the class. So just to make it more diverse, I'm gonna limit actually that only 2 students can choose the same topic. Okay, so the topic, so this limit will be applied separately to resident and DL student, because resident student, as I'm gonna discuss later, resident students are gonna present actually for the last 2 days of class. And DL student, well, they are gonna just kind of upload the record video, and then among DL students, they are gonna basically kind of share the videos within that group. Okay, so I'll create and share a spreadsheet where students can view the topics that have already been selected. So in the sense, if you choose the topic, you have to actually go into this Excel spreadsheet and write down the topic. Okay. Basically you are kind of securing the topic first. Okay, so if other students kind of wanna investigate the same topic, well, if 2 slots are filled, well, that student has to choose a different topic. Okay, so once a topic that has been selected by 2 students, it will no longer be available, and the student must choose a different topic. Okay, so in the sense that this is actually the link here. Okay, if you actually open the PDF file. By the way, this file has been uploaded on Sakai, right? You should be able to access. And then here, resident student group link and the DL student group link. Okay, for all of you here, you guys should use this link. But for DL student, they are gonna use this link. And then, it's basically opening up Excel spreadsheet. And if you choose a topic, just kind of write it down. Okay, so for any other students, they can take a look, okay, if the same topic has been chosen by 2 students. Okay. So again, the topic can be, anything. Okay, anything, it can be biology stuff, or it can be just kind of any any other stuff like coating or like just composite, any other materials. Okay, but it has to be relevant to nanomaterials or class of nanomaterials. So if you are actually uncertain about topic that you'd like to pursue, just ask me, okay, and then maybe I can guide you, or I can give you some other suggestions, or I'll say that topic is appropriate. Okay. So any questions about this topic selection? Okay, or think about it and then just ask me, like if you are kind of uncertain. Okay, so this is a suggested structure of the report. You can construct however you want. Okay, again, this is just kind of guideline. Okay, so you should have, but at least you should have title and abstract for sure. So the report should begin with a concise, informative title, and also the abstract should summarize the motivation and key properties, the method used to evaluate those properties, and the potential applications. And then it basically follows like other sections that look just similar to thesis work, right? Thesis paper. So here, introduction and the material overview, characterization techniques, unique properties and governing principles. So if you are actually kind of working on some modeling, okay, like mini review focusing on modeling of like nanomaterials, instead of characterization technique, it will be kind of modeling, right? The modeling part. And then you're going to describe some unique properties and governing principles, and then relevance to naval defense applications, and then summary and outlook, and then references here. Okay, so you have to provide at least 20 peer-reviewed references. So are you guys familiar with using like a Zotero, like bibliography software? Okay. If you are not familiar with it, I strongly recommend you to kind of learn about that, bibliography software, because it's very easy to use, okay, and then it's going to be very useful when you guys start writing your thesis, okay. So then when can you guys learn about that Zotero? Well, actually, library does offer like class or seminar, right? Or if you're not sure, like I ask you guys, ask just your friends, or even ask me. It's actually very easy to use. Okay. So for those of you basically don't feel why we need to use the key feature of that software is that as you guys are editing, sometimes you move the paragraph like a little later, or you move the paragraph earlier, right? Like you kind of switch the paragraphs. And then that reference gets automatically updated. The numbering is kind of automatic. Okay, so then if you don't use that, you have to manually change. Obviously, as you do manually, sometimes you make mistake, right? And then the reference, sometimes you say like 18, and then later on when you go look at it, those don't match. Okay, it's kind of creating a lot of kind of confusion. Yes.
You said it has to be peer reviewed. What if our thesis is a topic that is CUI, and we have access to previous written theses that we're continuing, but they're not peer reviewed because of their classification level?
Okay. But does that mean that it doesn't have a reference?
No, there is a reference, but it's not peer reviewed because it's CUI.
Oh, I see. So for those OCUIs, not peer reviewed at all?
I know Professor Ali doesn't release his research because he doesn't want China to see it. So I imagine.
Yeah, I understand. Yeah, but I thought that, okay, actually, I don't know about the answer, but my understanding was that even within the kind of classified research, there was some level of kind of peer review or kind of cross-checking. No?
I don't know. I don't think that our previous colleagues in this program released their thesis to get peer reviewed. I think they just do their thesis that has all the research that we're continuing. I haven't been told that my thesis has to be peer reviewed, so
by the way, all thesis work is not peer reviewed.
Right, so I'm thinking we use thesis work that we're continuing the research of, even though it's not peer reviewed.
I see. Okay, take a look at it, and then Okay, maybe some should be referenced, but like I think also some of them may be like publicly available, like research articles, right? Or do you feel like everything is?
No, I'm not saying everything. I'm saying,
Okay.
can we use past thesis work?
Yeah, I mean for that one, I understand. Yeah, I mean
As
that
a
one
part
is
of the
that one
20.
totally, yeah, that one is totally acceptable. Yeah, I mean, given your scope of work, yes, that's appropriate. Yes, that's fine. Yeah. So any other questions? Okay, so then the 20% weight for the final project is on final presentation. Like actually we have like 18 students in this resident class. Like so because of that, actually I mean before our presentation was 10 minutes long, but I had to actually shorten it, and it has to be 5 minutes. Okay, I mean it's a very short presentation. Basically in one class, 9 students will present, right? And then, another kind of class, the last year class, 9 students will present, okay? So in the sense, maximum slides should be 6, okay, no more than that. And so the delivery, again, the, in-person presentation for resident students, and then for DL students, video recorded presentation will be shared among the DL students, okay? And then the soft copy of the PowerPoint file or like a slide file should be uploaded to Sakai, by Monday, okay, by end of Monday, okay. And then this is suggested slide deck structure, title slide, and then like introduction, motivation, background. Again, these are just kind of a suggested one, but if you want to structure it differently, feel free to do so, okay. And then the grading rubric for final presentation and also the report have been uploaded, so take a look, and then as you guys write, basically kind of write such that like you guys meet those grading rubrics. Okay, so basically that's it for final project. Do you have any questions on this? Okay, so again, start thinking about the topic, and then like basically choose the topic that is relevant to your personal interest and the thesis work. I mean, if you can relate it to thesis work, it's a kind of win-win situation. Okay. All right. Okay. So then we will move on to this lecture part. Okay. So like yesterday we finished the infinite potential well, and then now we are getting into a new potential shape. Okay, so we are gonna actually reduce the potential height, from infinity to finite value. Okay, but before we get into that, I'm gonna talk about this theorem, because we are gonna use this theorem to work on finite potential well. Okay, so this theorem states that if the potential is an even function of x, just like cosine function, then psi, this wave function, can always be taken to be either even or odd function. Okay, so for this one, let us look into this time-independent Schrödinger equation. Okay, that is minus h bar square over 2m d square psi over dx square plus u of x psi x equals e psi x. Okay, we already know that, we've seen many times. And then here, just kind of we are replacing x with a negative x. Okay, so we are just kind of substituting. So with that, we can just rewrite this way. And then remember, like our assumption here is that if the potential is an even function, right? So basically, we are following this definition. Okay, if we satisfy this condition, that means it's an even function. So what that means is that u of minus x can be expressed as a u of x if this is an even function, right? So basically following this. So what that means is that we are replacing this u of minus x with u of x, because this is an even function, okay? So then we just simply write down here, okay? And then d of negative x squared is simply d over x squared, okay? And then here, we are going to take one more step for replacement here. We are replacing this psi of negative x with this big, like this big psi or big psi x. Okay. So what that means is that like if we take a first derivative, okay, so that means we have, this expression, and then negative sign comes out because we are taking derivative. And then if we take a derivative twice, and we have this expression, and then negative 1 comes out, and then, basically it's itself, right? Negative 1 squared is 1. So what that means is that now this expression can be expressed in terms of this big psi of x, and then now we get this expression, right? For example, look at this one. This psi of negative x is essentially this big psi x, and then same thing, but this part is also same as this one, right? So this is how we can express that. Then what is this expression? That expression itself is a Schrödinger equation, right? So look at this part. This is the Schrödinger equation. And then if you look at this expression, it's just kind of symbol is different, but the equation itself is exactly the same as Schrödinger equation, right? So what that means is that now if u of x is an even function, this psi of x and then psi of negative x is exactly giving you the same Schrödinger equation, okay? So what does it mean? Like now from here, we can actually construct even function and odd function using this psi of x and psi of negative x, okay? So how are we gonna do that? If we actually just sum up this psi of x and then psi of negative x, it actually gives you even function, okay? Here's a proof, okay? How are we gonna prove that this is even function? The way you do is that simply just kind of replace with the negative x here, okay? So then if you replace x with the negative x, this is essentially how we write, and then x replace with negative x, it kind of following here, and then here we are replacing with the negative x, and then negative 1, and then negative x there, right? So then if you look at this part, what is this? This is a psi negative x plus psi positive x, right? Which is just a starting point, right? So what that means is that psi even negative x just give you psi even x, right? So if you see this expression, psi even negative x and then psi even x, what is that? That is the actual definition of even function, right? So remember here, go here. If you can express f of negative x equals f of x, that is even function. Okay? So in the sense, if you look at it, since we get this expression, this one is even function. Does it make sense here? So, like I was able to make even function by summing up psi of x and then psi of negative x, okay? So anyways, if we move on, if we actually now subtract psi of x minus psi of negative x, this is actually odd function. We are going to prove that, okay? How? Again, we replace x with the negative x. So then this becomes psi of negative x, and then this term becomes minus psi of x, right? Because we are replacing x with negative x. So then what is this one? This is essentially, if we put negative sign out, it becomes psi of x minus psi of negative x. So then what is this one? This one is essentially psi of x minus psi of negative x is this one, right? This part. So in the sense, negative psi odd x. Yeah? So then look at this one. Psi odd negative x equals minus psi odd x. That is essentially the definition of odd function, right? So in the sense, you plug this psi even and psi odd into Schrödinger equation again, and then you will see that when we plug it in, this is essentially kind of expression, full expression. And then, from the previous page here, that psi of x, okay, when we just combine, when we just kind of extract the psi of x part, it gives you Schrodinger equation. And then when you extract just psi of negative x, it gives you Schrodinger equation. Okay, so in a sense, this one is actually Schrodinger equation. Okay, and the odd part is the same thing. Okay, so in the sense, basically, like, because even and odd are linear combinations of psi of x and psi of negative x. This even and odd are also solutions of Schrodinger equation. Okay, so with this argument, what we are gonna basically come up with is this psi of x by looking at this one. Okay, so we have even function expression like this and odd function expression like that, and then from here we can extract the psi of x, right? How do we do that? We sum up even function and odd function, then this psi of negative x cancel out, right? And then we have 2 psi of x. So psi of x is essentially 1/2 psi even plus psi odd. Okay. So what that means is that now any solution can be written as linear combinations of even and odd solution if this potential is even function. Okay. So again, we kind of went through kind of lengthy proof, but the final statement here is that if potential is even function, that means we can consider just even solution part and odd solution part, and then we can combine them later. Okay, so that is essentially kind of statement, and we are going to use this theorem to work on finite potential well. Okay, so let us look into the specific problem we are going to work on. Okay, let us look into finite square well. So this here, let us let me just kind of draw the problem statement first. And then this is a u of x. And here, minus a. Okay, this is a problem statement here. So our potential constraint is given like that. Okay, so think about the bucket here. Okay, so bucket now shape or height is finite. Okay, because bucket height in this case is this is 0 point, and then this is negative u naught. So the bucket height is only u naught. So the previous case, the wall height was infinity. Do you remember? Okay, so in this case, we are kind of looking at the finite sized wall height, and now we are placing the particle within this bucket. Okay, again, this is still within the bucket. Okay, so imagine this is essentially, the finite sized bucket, and then within that bucket we are putting in like particle. Okay. And then we are going to look into how this particle behaves. Okay, so we are going to look into again the energies that this particle can take, and then the position and velocity, etc. Okay. So, but anyway, so here we are going to really focus on the energy. Okay. So, with that, let us now look into this particle. And then this particle, the energy is essentially given, or we just state that as E, okay? And then this is a particle. Or you can also think about this as kind of wave, because, like a particle has also wave characteristic. So what that means is that here, the energy difference between the particle energy and the bottom of the well is energy minus u naught is E plus U naught. Okay? We are looking at this energy difference. Okay? And then here, also the potential description is that we have minus U naught when X is greater than minus A and smaller than A. And then the potential is 0 otherwise, okay? So again, in this case, the potential outside of the bucket is 0, but within the bucket, the potential is negative U naught. Okay, that is a problem statement. Okay, so the potential description, because in order to solve Schrodinger equation, we need to know what this U of X is, right? So here's 0, and then negative U naught, and then 0. And also in this particular case, the particle of energy, or the energy of particle must be larger than minus U naught and then smaller than 0. Okay, so now the condition is that the energy of the particle has to be situated between the bottom of the well and then the top of the well. Okay, so it has to be within that. So like a particle is not located here, or particle is not located here. Okay, it must be between the bottom and the top of the bucket. Okay. So again, with this problem statement, we need to look into 3 regimes. Okay, the first regime is when X is smaller than negative A, and second, we have to look inside cavity or well or bucket. And here, 3, X is larger than A. Okay? So in the sense, if I kind of draw it here, this is a regime 1, right? This is a regime 1. And then regime 2, this is a regime 2. And then regime 3 is essentially here. Right? We have to look into these 3 regimes, okay? Because for regime 1, we have a potential 0, and then for regime 2, we have a potential negative U naught, and then third regime, potential 0, okay? And also, if you look at this potential description, you can tell whether it's an even function or odd function, right? The potential description here is even function. Do you see that? Huh? Do you see that here? U of X is even function. So what it means is that we can use the theorem that we just kind of proved. Okay, so let me just kind of write down. U of X is even function. Okay, because it's like a mirrored along this y-axis, right? If you look at this one. So what that means is that we can really look into even solutions and odd solutions, okay? And then that's essentially what we are going to do. And then let us look into the regime 1, okay? So regime 1, so that is essentially X is smaller than negative A, okay? So we look into this regime, and for that one we have to solve the Schrodinger equation. Right, and then if we write the Schrodinger equation, minus h bar square over 2m d square psi dx square plus u psi, but we already know that u is 0, right? We already know u is 0 in this regime because it's 0. So I'm gonna kind of skip this one, and we write down as e psi, okay? And then if we look into that, minus 2me over h bar square psi. And then here, we are going to use this. We are going to denote k here. That is square root minus 2me over h bar square. Okay, so in this case, d square psi dx square can be written as k square psi. Okay. By the way, if you look at this one, this k variable, what is the sign of e? What is the sign of e? So if you look at it, e, the sign of that is negative value. Okay, just from the problem statement. So in the sense, since this e is negative, this one is a real number. Okay, I just want to make a note here. This is not imaginary number because e has to be negative. Okay, that is essentially from our problem statement. So this k is a real number. Okay, I just want to make a note here. And then, like if we solve this differential equation, the solution form is a times exponential minus kx plus b times exponential kx. Okay, this is a solution form. Okay, and then now let us look into this one. Okay, so now for the region 1, if we look at the psi is related to probability density function. Do you remember? Okay, so then, when we look at this regime, let's look into, like when x goes to negative infinity. Okay, because, like we are essentially covering the whole regime here, right? When x goes to infinity, you will notice something here. When x goes to negative infinity, this one goes to 0. Well, what happens to this first term? K is a real number, right? And then when x goes to negative infinity, this one goes infinity, right? Does that actually physically make sense? Because like when we look at this wave function, this is related to probability density function, right? So we will evaluate eventually psi star psi, right? But if this psi becomes infinity as we go to like a negative infinity, psi star psi will also give you infinity. What does it mean, for probability being infinity? That doesn't make sense, right? Are you guys following the kind of my logic here? Because it's kind of blowing up here, the only condition to kind of make this sense is essentially a has to be 0. Okay, this is kind of like a like a boundary conditions. Okay, because as x goes to negative infinity, this one goes infinity. That doesn't make sense, right? Because we are going to look at actual probability, right? Probability density function. It cannot be infinity, right? What is a probability being infinity? Okay, so in the sense, this one has to be 0. Okay, so a has to be 0 because it blows up. Okay. Okay. So then another thing is that let's say a is 0, okay, but we have some value here, right? We have this one. Obviously, we will eventually evaluate this b and any other term, but we have some expression for psi. So what does it mean in terms of probability density function in regime 1? That means we are going to have some probability value even in region 1. Does it make sense? Huh? So this one is actually kind of a big difference between infinite potential well and finite potential well. Infinite potential well, what was the probability of finding the matter outside of the wall? 0, right? But in this case, we are going to deal with some probability. Okay, and then that one we are going to actually come back and we are going to talk about it. And then, this one must be confusing you, okay? Because, actually, maybe I'll just give you a brief description what happens in the kind of bulk scale object. Imagine we have a bucket, okay? And then you put the ball inside the bucket. Can you find the ball outside the block or outside of the bucket ever? You cannot, right? If you put the particle inside the bucket, and then the particle is located below the top of the bucket height, you will never find this particle outside of the bucket, right? That is essentially kind of our observation for bulk scale object, okay? But there is something interesting that will happen when we consider microscopic object, electrons, okay? So that is something we are going to come back, okay? And then this is essentially kind of related to like electron tunneling. Have you guys heard about that? Okay, that is essentially kind of like what we are going to talk about, okay? So just wait for that. So anyways, here, just by looking at this x going to negative infinity, at least we know that a has to be 0. Does that make sense here? Okay. So then, now let's go to the regime 2. Okay, that is essentially x is larger than negative a and smaller than a. And for that one, we again write down Schrödinger equation here. And then here, plus u of x, but we already know the potential energy, right, for this regime, because that is minus u naught psi equals E psi. Okay. So general equation for Schrödinger equation here is that plus u of x, but we already know that for this regime 2, that u of x is negative u naught. Okay, so this is why we are writing it down like that. And then this one can be rewritten as, or like, let me just kind of simplify even more. d square psi over dx square equals, by the way, this u naught is constant, right? It's no longer variable, so we can actually move to the right hand side. That means it's now minus 2m e plus u naught and then over h bar square psi. Okay, I'm moving this term to the right hand side, okay, e plus u naught, and then I'm moving this one to the right hand side, and then this is what we get. So here again, another thing, this e plus u naught, we have to evaluate the sign of that. Okay, we have to evaluate the sign. So for that one, let's just go back here. Okay, so if you look at it, e plus u naught is simply what? Energy difference between the particle energy and the bottom of the bucket. Okay, so e plus u naught is actually positive value always. Does that make sense? Because it's always the energy difference between the bottom and the particle energy. So E plus U naught is positive. So in this case, what we are gonna do is, we are replacing we are introducing one variable L. Okay, let me introduce. That is 2m E plus U naught over H bar. Okay, square root. 2m E plus U naught over H bar. And then from this one, d square psi dx square becomes minus L square psi. Okay? Because here, since this one is positive value, we are putting just negative sign there, and then we are just using this real number. Okay? So that is why we have negative L square psi. And then from here, what is the solution form? That is C times sine Lx plus D times cosine Lx. Okay? By the way, here, like A, B, C, D, these are all unknowns. Okay, all unknowns. That is something we need to evaluate later. Okay, so we got the general solution for regime 2, and then now we are going to work on regime 3. Okay, so here, regime 3, that is essentially x is larger than a. The same thing, right? I mean, it's the same expression for regime 1. Okay, h bar square over 2m d square psi over dx square equals e psi. But since we are working on different regime, right, other than regime 1, we will get separate equation here, that is f times exponential minus kx plus g times exponential kx. Okay? So again, we can use the same argument. Okay? So we actually look at this wave function. Now you can kind of tell which unknown has to be 0, right? So in this case, we are looking at regime 3, so essentially x larger than a here, right? Probability density function has to be finite number. So in the sense, like if we actually kind of substitute this x going to infinity, which term blows up in this case? Now the second term blows up, right? This one is going to infinity. This one goes to 0, this one goes to infinity. Then it doesn't physically make sense because, like again, this gives us the probability being infinity, okay? So because of that, g has to be 0, okay? Because, if g is not 0, physically it doesn't make sense. Does it make sense? Okay. So with that, okay, so now we got the solution here. Okay, so basically g goes to 0 here, this term, and this term goes to 0. So then we have the solution, right? For regime 1, we have this part, and then for regime 2, we do have the 2 terms, and then for regime 3, we have that. Okay. So in the sense, like now we are gonna kind of consider just the even solution. Okay, first consider even solutions. Okay, because for our case, the potential energy was even function, so like we can take psi to be either even or odd. Okay, and then later on we can just combine. So let's just consider even solution first. Okay, so this is essentially we are using theorem then just provided. Okay, and then so for even solution is essentially when x is larger than a, that's a regime 3, we have this expression f times e to the minus kx power. And then when x is larger and then smaller, larger than 0 and then smaller than a, that is d times cosine lx. Right. So here this is a regime 2, but like look at this one, regime 2. This is the expression, but we are only considering the even solutions. Okay, so in this case, what is the even part? That is cosine, right? Cosine. So we are taking this cosine here, and then because that is just only even solution, and then when x is smaller than 0, we can simply mirror that image. Okay. So that is essentially even solutions.
Should those zeros be negative a's?
So that one is a kind of same thing because like here x is larger than a, and then this one is we are covering from 0 to infinity, right? And then since we are only considering even solution, negative x part we are going to just mirror this graph.
I thought our bucket went from negative A to
Right.
positive A.
Yes. So in this case, I mean, this is basically same thing here. Like if you look at it, this one is going to look something like this one. But here we are only considering even solutions. So for example, look at just focus on this positive part. So it's going to look something like, since this one is cosine, like I'm going to just kind of focus on the positive value, positive side, okay? In this case, how it is going to look is something like cosine, and then this one is exponentially decaying feature, right? Something like this, right? And then for negative side, what we are doing is essentially we are mirroring. So in the sense, we have just the same feature from negative A to A. But this one is essentially kind of we are mirroring.
Well, even if we expanded it from negative A to A, cosine is still an even function, so it would still be symmetric across it, and then from negative A to A, it would just be the B.
Yeah. I mean, the same argument. So that's why, I didn't actually write down the full expression. I just wrote down as a plus side over negative x. So in the sense, yeah, your argument is exactly right. So here, it's going to be still cosine, and then below negative A, it's going to be, again, exponential decay. Yeah. Okay, so with that, let me just kind of move on. Okay, so in this case, again, we have to kind of find the unknown values. Okay, how are we going to find unknown values? We have to again use the kind of boundary conditions. So in this case, boundary conditions are continuity of psi of x at this crossing point. Okay, so at x equals a, these two functions has to meet, right, to make a continuity. So if we do that, that is essentially f times e to the minus k a equals d times cosine LA. Does it make sense? Because it has to flow continuously. And also another part here is continuity of d psi over dx at x equal a. Okay, in this case, again, not just for psi of x, we have to meet continuity of the slope. Okay, slope has to be identical. Okay, so in this case, if we take a derivative, there's a minus k f e to the minus negative ka equals minus l d sine la. Okay, so let's say this is a first equation and this is second equation. Okay. So again, this boundary condition is essentially, I deleted it, but if we look at it, 0 and a, whatever it goes here, cosine, and then there is an exponential decay one. At this particular point, right, at this boundary, it has to meet continuity, right? The point itself has to be, kind of continuous, and also the slope has to be, continuous. Yes?
Why does the slope have to be?
Say again?
Why does the slope have to be? Was that just a bad English we were given earlier?
So in this case, we actually have two unknowns, right? So we have to actually find out at least two independent equations to find out unknowns, right? So the first one is easy to get, right? I mean, this one probably makes sense, right? And then we have to find the second boundary conditions. In this case, what we can use is that, we typically use this slope continuity. Because, as we kind of draw like that, we have to also match the slope. If the slope does not match, what does it mean? It's going to look something like kind of a very, like something like this, and then here like that, right? So we cannot really draw like that. So this is why we are actually matching the slope as well.
Is that just because that doesn't happen physically, that sharp corner?
That's right. Yes. Yeah. Okay. So yeah, with that, we can end today's class, and then we'll continue on next Monday.